Hello everyone, my name is Chong Jie and today I'm going to explain on how am I going to do lab 3, the routing protocol. So the introduction, we're going to start to do the lab 3. So now this is an introduction. So you are given a packet tracer file which requires some work IP addressing and routing protocol configuration. You must follow all the steps carefully and answer the given questions. So this is the topology given in figure 1. So I already opened the packet tracer file here. So as you can see, it's actually kind of similar. Yes, it's actually similar to what is provided to us in the packet tracer file. So okay, moving on to task 1 of lab 3. So this is task 1 we are going to learn about IP addressing. So step 1, fill in table 1 below with the correct information. Note, the information may be found under the config tab of each router. Refer to figure 2. So this figure 2, so in order to, okay, before that, let me just see what do I need to answer. So I think I need to refer uh, each each router here, and then determine the IP address of each interface and the subnet mask also. So in here there are 3, 7, and 9. So I need to fill in 9 items here. Don't know why this is wrong. Let me just fix it real fast. Okay, in order to find the IP address for for these interfaces respectively, I had to go to each router, go to the config, like the question mentioned about it. So now if I go down here, so it requires me to find the interface SE2/0. So SE2/0 means it's the short form for serial 2/0. So as you can see here, this is the IP address. This is the IPv4 address. We're just gonna copy it. Let's paste it here. Actually, before that, let me just do this. Change it to blue, so it's indicate that it's the answer. So I'm just gonna slowly but surely complete this table here by just opening each router, go to config, and then try to match the IP address with the interface mentioned in the table here. So here's the subnet mask. Let me just copy it again, paste it in. So this will be the subnet mask. Okay, and then afterwards, FA0/0 means that it's fast Ethernet 0/0. So this interface here has a IPv4 address of this number here, and the subnet mask. Here's the subnet mask of this interface. So moving on to FA1/0, go to this one because it's fast Ethernet 1/0, and this is the IP address for it, and alongside with its subnet mask. So I think we are done with router B. So moving on to router C, we have 4 interfaces that we need to find the IP addresses and subnet masks. So close the router B window and then open up router C, RTC, go to config tab and then try to match the interface. So SE2 2/0, so it's serial 2/0. So this is the IP address for it. So, and then this is its subnet mask. So moving on to SE3/0, this is serial 3/0. So copy this, copy this also. So and oh sorry. So afterwards, go to FA0/0, and then it's fast Ethernet 0/0. So copy this one. I just use the hotkeys, and then this is subnet mask for the subnet mask. Sorry, the subnet mask for this interface here, fast Ethernet 0/0 interface, and the interface FA1/0. Go to here in order to find the IP address for it, and then this is its subnet mask. So now I'm done with RTC. So moving on to find the IP addresses for the interfaces in our RTD. So I already opened the RTD. I just opened the RTD window. Go to config tab, and then let me just find the interface. So SE2/0. So this is the one that we need to find, and then this IP address for it, and then this will be the subnet mask for this interface. So the last one is FA0/0. So fast Ethernet 0/0. So this will be the IP address for it, and this will be the subnet mask for the interface. So this will be it for the table part for step 1. So moving on to step 2, given the information in the file, for the following questions. So step 2A, how many subnets are there? So in order to determine how many subnets, I'm just going to show it. So this is one subnet here, this is one subnet, so this is one subnet. So anywhere that is connected to the interface of the router, considered as, actually it's just it's easier for me to show you guys how is it like considered as a subnet. So this one entire thing is a subnet, and this is subnet 1. Sorry. So in total, in order to find how many subnets is within this topology, we can determine it like this. So this entire thing counts as one subnet. So this is one subnet, this is two subnets, three subnets, four subnets, and then between routers also counts as one subnet. So there's a fifth subnet, the sixth, there's the sixth one, the seventh, and the eighth subnet. So in total, there are actually 8 subnets only in this topology. So let me just delete the line there, and then make it bold blue to indicate the answer. So step 2B, what is the network address of each of these subnets? Hint, given the IP address and the subnet mask, you can calculate the network address using AND operations. Label the subnets in the topology given in figure 1 and complete the table below. Complete table 2 below. So this table 2 is already given us 2 subnets already. The information about 2 subnets already. So the first subnet has a network address of 172.16.224.0, and this its broadcast address. So 172.16.225.255. So let me just make it bigger for us to look at it easier. Excuse me. So moving on, actually there's only 2. So since out 8 subnets, there's already like 2 subnets given by the question. So Oh, actually, let me just show you how to actually like find find the network address using the AND operation. So actually, I already like did it. Actually, I already did it. This is my calculations for it. So in order to find it, in order to find the network IP address of each subnet mask, sorry, of each subnet, sorry. So you have to first, uh, how can I say? Uh, Let me just see. So I just gonna, because I did the calculations based on this table here. So the IP address number one IP address, I will just take it and I will just turn it to binary first, and then secondly I will turn the subnet mask also into binary. So for the first one, it's 172. Uh, the first one, sorry, first one has an IP address of 172.1.230.5. Is the IP address in decimals, and then this is subnet mask also in decimals. So the subnet mask is 255, 255, 255, and 252. So we convert all of them into binary, and then we AND operation and then we perform AND operation on both of the binaries. So 172 turns into 172 in binary is 10101100, and 255 in binary is 11111111. So when we perform an operation, so 11 equals to 1, 01, when perform AND operation will become 0. So you actually like repeat the process until you get the result. So the result will give you the network IP address. So the only thing like really matters is like the back part here, because if you realize that if I do all the like AND operations, in this case, in this case, um, all the AND operation I did is actually lead to the same like same. The only thing it's the same for like the 12 numbers here is the front two numbers. Only the back two numbers actually change a bit. So I can scroll through down my calculations. So also if you perform AND operations on two zeros, it will still become a 0. So that's a thing that we need to know. So after calculating the subnet mask, sorry, the network address of this subnet mask, sorry, let me just think about it. So using AND operations, and then calculate and then using the IP address, all the IP addresses and subnet masks in this table here, I already determined all 8 of the subnet, all network addresses of all 8 of the subnet. So actually, let me just fill in the numbers here first. Let's fill in the numbers here first. Middle. It's only 8. It's 1, 2, 3, 4, 5, 6, 7, 8. So since here we already have, actually, let me just do it based on my calculations here. Since I already did it here actually, so I just already scan it there. Is my calculations here, in case you're wondering. place it there just for like looking at it like easily, more easily to look at it. So based on my first using the first network IP address, using the first IP address, we can determine that one of the subnet has a network IP address of 172.168.230 and 4. So it's 172. You can just I just refer here because it's easier to see. So 172.16.230.4. And then since the first one has a subnet mask of 255, 255, 255, and 252, we can actually know that it only actually has around four IP addresses because this has a subnet mask of /30, or you can just or it's just you can write it like this, or you can just write it like /30 actually. But in this case, we're going to use this one because we have to calculate the network address part. So the broadcast address is actually like 172.16.230.7. So the only usable addresses is actually this range here. So there's only like around two, actually not around. There's only actually two usable IP addresses in this subnet here. So I know that this is the broadcast. I know the broadcast address because by looking at the subnet mask, it's actually like previously I said that /30, right? So in order to determine how many IP addresses is left for us to use, you can just do this. So 2 with the power of 32. Actually, it's better to do this. Minus the subnet mask, in this case 30 for the first one. So it's equal to like 2 with the power of 2. So you know that 2 power with the power of 2 is equals to 4. So in this subnet, it only contains like 4 IP addresses, and only 2 of them is only usable by the host. So that's the entire process of how to like find the network address, the broadcast address, and the range of usable IP addresses for like one subnet. So I'm just gonna do it. I'm just gonna do the rest based on my calculations. Here, and then I already pasted like I previously mentioned. So moving on to the second one, we have a network IP address. Moving on to the second IP address, by using the AND operations, we can determine that the network, the subnet network IP, the the network address for the subnet for the second, using the second IP address is 172.168.230 and 0. So it's already here. So actually it's already like it's already provided to us already at this row here. So we don't need to like write it out. So moving on to the third calculation using the third IP address. So using the AND operations, using the AND operation, we can find that the network IP address is 172.168.240 and 0. So if we refer to this, it's already also provided to us here. So that's another one that we don't need to like write it down. So moving on to the using the fourth IP address. After using the AND operation, we can find that the network IP address is 172.162.3.0 and 0. So this IP address here resides under this subnet here. So we don't really need to write anything else because it's a duplicate. Because it's a duplicate now. So moving on, using the fifth IP address to do the calculations. So the fifth one, they give a result of 172.162.3.0 and 8. So that's a new one. So if you refer here, there's a new one. So there's a new one. So that will be the network address for the fourth subnet. And just do this real fast. So this is the network address, and then let me just refer to the subnet mask. The subnet mask is /30/30, the fifth one. So /30 means the last number here should be 252. So the fifth one is here. Yes, here. So there's only like four IP addresses in this subnet. So the broadcast address will be 172.16.230.11, and the usable range of IP addresses is 9. The last 10. So that's everything for the subnet 4. And then moving on to the fifth one, we have to like go to this one here. So moving on to this doing the calculations using the 6th IP address. The result I got is 172.162.26 and 0. So that means there's a new subnet mask. That's the IP address of a new subnet mask. So 172.226.0. And then just now we can see that it's actually have subnet mask of /23. So we do the math. I'm just gonna do the math very fast. So 32 minus 23 equals to 9. So 2 with a power of 9 it equals to 512. So that's actually like it's a big range. So the IP address for the broadcast is 172.16.227.255. And then the usable range is very big. So I just have to like copy this because it's similar to it. And I will use the usable range. That the lower limit is 172.16.226.1, and the upper limit is 172.16.225.254. Oh, sorry, it's not 225. It's actually 227. So that is everything for subnet mask 5, and then moving on, doing the calculations using the 7th IP address. So the result is 172.162.30 and 4, which is also a duplicate since you already have it in our subnet in our table here. So moving on to using the 8th IP address. So the result is 172.162.30.12, and it has a subnet mask of /30, which means that first, this is a new subnet, and secondly, this subnet contains only like four IP addresses. So let me just enter the information inside into it. So let me just copy that. 12, sorry, 12, and then 15. Since it only has, so it has a subnet mask of /30. So it's similar to this. Let me just copy that. Let me just change the numbers. So the lower limit is 172.16.230.13, and then the upper limit is 172.16.230.14. So that's everything for subnet mask 6. So moving on moving on using the 9th IP address. So after doing the calculations, we can know that the IP address, the network address is 172.162.30 and 8, which is also a duplicate, since already I have it here. And then moving on to doing the calculations using the 10th IP address. So we get the result of 172.162.28 and 0. So that's a new subnet mask. Sorry, that's a new network address for the subnet, and then this is the subnet mask /24. Or in here is 255.255.255.0. So this is a new subnet. So 172. Actually, already did that. 172.168.228.0, and then since it has a /24, something mask of /24, so 32 minus 24 equals to 8. So 2 to the power of 8 equals to 256. So that means the broadcast address is 172.16.230 .228.255. So the range of usable IP addresses starts from 172.16.228.1 until 172.16.228.254. So that will be everything for the 7 subnets. Now we have to find the last subnet. So doing the calculations using the 11th IP address, we can find that the network address IP address is 172.162.30 and 12. It's a duplicate, since you only have it here. So we're gonna move on by doing calculations using the last IP address provided. So by using the 12th IP address, we can find that the network IP address is 172.162.29 and 0. So this is a new network IP address for a subnet, and then this is the subnet mask /24. So /24, yes. So 172.16.229.0, and then similar to the 7th subnet, it has 256 IP addresses within it. So 172.16.229.255 will be its broadcast address. So the usable range is actually similar to the 7th subnet, but instead of this like 228, we will change it to 229. So afterwards, since we already done all the calculations here and then we use all 12 IP addresses, so I think we already done with the step 2b. So I think afterwards I will continue on discussing discuss I'm sorry the discussing actually like I can just discuss it now. So provided that all PCs will use the last usable address in its subnet, fill in the table tree below with the correct information. So step 2c, by reading this information here, provided that all PCs will use the last usable address in its subnet, fill in the table tree below with the correct information. So it's already given for us PCA, this IP address with the subnet mask, and then the default gateway. So PCB, let me just see the thing first. So let me just determine the default gateway first. So the default gateway for PCB is actually, just check it first. Actually, I don't need to check this first. Like this, very fast. So by hovering over this, you can briefly see the interface here. So if this wire here is connecting to the interface FA10. So FA10 is fast Ethernet 10. This is like its default gateway. So this is the default gateway. So this is the subnet mask of the default gateway. So this is the subnet mask for the default gateway. Paste it. And since it's the default gateway is this one, this IP address, so I'm just going to have to refer to the apps in here. So let me just refer to the default gateway again. So default gateway is 172.16.226.11. So it's within this subnet here. So the IP address for this one will be this. The IP address for PCB will be this one. Oh, let me paste it. So that will be the answer for PCB, and then for PCC it's like the same process. I will just look at this first. So it's so in this subnet, it's using the FA10 1/0 interface, fast Ethernet 1/0, and then this will be the default gateway, and then this will be the subnet mask. And afterwards, let me just see. And afterwards, you can find the IP address for this one. So on this instance, so let me just see the default gateway again. 172.16.228.11.11. I mean. So it's under this subnet here. So the last usable one is this one. Is this IP address here. So moving on to PCD, since you're already done with PCC. So PCD, let me just go to PCD first. It's located here, and then let me just see the interface connected to the router. So it's FA0/0. And then go to here, go to the config again. So it's FA0/0. Let's check it again actually. FA0/0. So that means that this is the correct one. So this is the default gateway. This is the IP address for the default gateway, and this will be the subnet mask for it. So the default gateway is 172.16.229.222. So it's under this subnet here. So the last usable IP address is this one. So PCD will have this IP address 172.16.229.254. So I think that will be all for step 2. I'm going to explain how to do step 3 afterwards and onwards. Now I'm going to continue on doing step 3. So in step 3, complete the IP addressing information on all PCs in the topology. Hit click on the PC, choose the desktop tab, then click IP configurations. So I have to manually configure like the IP addresses to each PC in the topology. So let me just start with PCA. Go to PCA, go to desktop, go to IP configurations with the instructions set. So this is the interface, and we just have to like focus on these 3 things. So this is the IP address. And just assign it first manually to the PCA. So they just copy like everything and paste it to their respective blank spaces. So that's probably all for PCA. And moving afterwards to PCB, go to the same thing, desktop, IP configurations, and then copy the IP address here. Copy the subnet mask, then copy the default gateway. Actually, subnet mask is not complete. It didn't. Okay. So this is the IP address, this is the subnet mask, and this is the default. Okay, wait, let's check it a bit. Okay. That will be it for PCB. PCC, click on the PCC, go to desktop, go to IP address configurations, copy the PCC IP address, subnet mask, and then default gateway. So this will be it for PCC. PCD. So go to desktop, go to IP configurations. Oh no, do that. Go to this thing, copy this, paste it in here. Copy the subnet mask and paste it in here also. And copy the default gateway and paste it in its respective blank spaces. So that will be all. So PCA, go to IP configurations, check it again, just matches, go to PCB, IP configuration, just check it. It's correct. PCC is correct. And PCD configurations. And that will be it. So I check out everything, so everything should be correct. So step 4, open the routing table for each router. Hint, you can use the magnifying glass icon, then point to a router and choose routing table. See figure 3 below. So I will be using this one, this icon here. And then I have to open each routing table. So pick on the router. We just start with router RTA, router B, TB, RTC, and RTD. And since I open all of them, just arrange them nicely here for now. And then step 5, copy the image of the routing table for each router. Hint, you can use the snipping tool to copy the images. So let me just do that. Oh, sorry. Just do that accordingly. So let's do that. So RTA. Wait, let's do this. Check upstairs. So RTA, RTB, RTC, and RTD. So make them all bold, and then make them all have blue color. So RTA, this is the routing table for RTA. So let me just snip it for now. This will be the first one. This will be the routing table for RTB. This will be routing table for RTC. And this will be the routing table for this is RTC. RTC. And the last one is the routing table for RTD. So I think that will be all for step 5. So moving on to step 6, answer the questions below. So step 6A, do all the routers have the same information in its routing table? You can see here the routing table A, B, C, D. So the answer to A is no. It's no. All routers have different information in their routing table. Bold. And afterwards, what is the difference that can be seen? So what is the difference? So the amount, you can see that RTA and RTB had the same amount of networks but different ports. RTC, RTD have different number also and have different ports. So the difference is, let me just answer this. For step 6B, the difference is the amount of networks and port use. The difference in the routing tables is the amount of networks and port use in each routing table. That will be the answer for step 6B. And step 6C, can all the PCs ping each other successfully? So in order to do this, I have to go to change back to the default mode, like using select. And then I have to go to PCA first, since the question asked me to ping between devices. So go to command prompt, ping. Let me just find the IP address for PCB. And then ping. Oh, I have to use this paste. So enter. So you can see that PCA is trying to ping to PCB, but destination host is unreachable. That means it's unsuccessful. As for PCA to PCC, so I have to ping again, but this time using the IP address for PCC. So PCA is trying to ping to PCC, and 100% loss, like how it did for PCB. Another X to indicate it's unsuccessful. And moving on to find PCA to PCD, and then so ping PCA to PCD. Enter. The first reply is unreachable, destination host is unreachable. Timeout. So it's similar to the above two, where PCA is unable to ping to the other three PCs, since all the packets are lost and since the destination host is unreachable. So that is all for PCA, testing for PCA. Now I'm going to test for PCB. So go to PCB, go to the command prompt, similar to how I did for PCA, go ping, and then ping PCB to PCC now. So wait for a bit. As you can see, PCB is unable to reach, the packet sent from PCB is unable to reach PCC. So we get the results similar to how the previous three ping command. So moving on to PCB, trying to ping the PCD. So ping to PCD using this IP address. So paste. So similar to the previous four, so 3 destinations unreachable and 1 request timeout. So it's also deemed unsuccessful for PCB to contact to ping to the other PCs. So now we are going to test out on PCC. So going to PCC, go to the command prompt, then try to ping to PCD. So PCD actually already have the IP address. Yeah, so let me just enter it. First reply, destination host unreachable, same as the second one. So the third one, request timeout, and the last one is destination host unreachable. So all 6 of the pings between devices like PCA, so all the PCs are unable to ping to each other. So that's so all of them are unsuccessful. And then afterwards, moving on to step 6D, reflection. What is the reason for your answer in C? The reasoning is all destinations are unable to reach. So the reason is devices are unable to establish. Actually, let me just word it this way. There is no complete there's no established route between devices. There's no established route between devices that packets. There's no established routes between devices. Thus, all packets are unable to reach their destination due to not knowing where the destination is. So that will be my answer for step 6D. So I think that will be all for task 1 IP addressing. And then afterwards, I will continue on explaining step 3 task 2 dynamic routing configuration. RIP or the full name is routing information protocol. So now let me just continue on doing task 2. So lab 3 task 2. So in task 2, we are required to learn about the dynamic routing configuration, RIP, or the full name is routing information protocol. So dynamic routing allows the network to be more flexible to changes. It can help the routers to adapt to the changes in the pathways without much intervention from the network administrators. In this part of the lab, you will learn how to configure a RIP routing protocol and see how changes happen in the routing tables. Routers R1 and R4 is already configured for you. So step 1 of task 2, choose router RTA, click the actually let me just do one by one. So choose the router RTA, click the CLI tab, copy the following text into the command line interface. So go to CLI tab here, RTA, and then afterwards, let me just actually start to configure the router. So in order to do it, first off, start by pressing enter, and then start type in the bold words. So first one is enable, and enter. You can see that this symbol here changed to a hashtag. So configure terminal, enter. So it will bring up this more lines of this. So now the configure. Continue on following to the end. So afterwards, router RIP version 2, and then this one, let me just copy it just in case. So copy, and then use this to paste it. Enter afterwards, and then no auto summary. Afterwards, I can just type in exit and exit. Two exits here, and then afterwards, let me just type in enter again, so that RTA will appear, and then afterwards, copy this one, and then paste it here, and that will do, and then enter again. So I think we are at the end of the configuration that I should be configuring. So let me just actually let me just I guess I'll just close it, and then task 1.1, copy and paste the RTA routing table here since I already configured. Just do that. So to the magnifying glass icon, click on the magnifying glass icon here, click on the router, click on the routing table, and bring up the routing table for RTA. Let me just snip that, close it, and enter. So this will be the answer for task 1.1a. Then step 2, choose router RTB, click the CLI tab, so it's router RTB. And afterwards, copy the following text into a command line interface. So RTB, actually RTB. Let's check a bit. So RTB, we have these lines of code here. actually doesn't really matter now. So start by entering enable configure terminal router RIP version 2 network. Actually, this one, let me just copy it, paste it in, and no auto summary. Exit. And afterwards, enter again, and type in this, copy this line here. Yes. So that will be done for step 2, and then task 2.1. Copy and paste the RBT routing table, and then take a new look into our RTA routing table here. So I had to take two pictures. So I have to close this. So go to inspect. Sorry, click on the magnifying glass. Inspect. Go to our routing table for RTB. Then go to table for RTA. You can see that previously RTA has only 3 networks here. Now it has 5. So same as RBT. The routing table RBT is also have 5 networks here. So let me just do this RBT new RTA table. So let me just actually get it. So this will be the new RTA routing table. So I think that is all for task 2.1a, and then moving on to task 2. We're on to task 2.1b, reflection. What is the difference you see between the routing tables of RTA and RTB? So my reflection is, actually, okay. So my reflection is, the type R route, the number of network in RTA increase. Number of networks in RTA has increased. So that's the first thing that we notice. And then the second thing is because, and this is due to the type R. The type R route is dynamically learned by router RTA from RTB through the RIP. Yes, through the RIP. So technically speaking, in simple terms, the reason that RTA routing table has increased network is because that the type R routes mean that router RTA learns the IP address of these routes through RTB, router RTB, by using the routing information protocol. So that will be my reflection. That will be my my answer for task 2.1b. So moving on to step 3, copy the same configuration instruction to RTC and RTD. So I will do that now. So let me just click select, go to RTC, go to the command line, and then afterwards go down here, and then afterwards I will just repeat my steps, like how I configure for RTB and RTA. So configure terminal, and then router RIP version 2. This one, let me just copy it. Then no auto summary, exit, then let me just enter it, and then afterwards copy the running config, startup config. Copy this, paste it here, enter again. Okay, so that that's all the configuration I need for RTC. So moving on to RTD, moving to the command line interface, enter to start, enable, configure terminal, enter. Okay, router RIP version 2, and then this one, we just copy this, paste it in here. No auto summary, let's copy this actually. So exit, and then afterwards enter again, paste this line of command here, and then enter again. So I have done step 3. Now I'm going to move on to step 4. Let me just close this. So in step 4, answer the questions below. So question 4, do all the routers have the same information in its routing table? And in order to answer that question, let me just bring up all the routing tables first. Let me just arrange them neatly here. Actually, let me just do this actually. Do this so it's easier to see. So we can see that RTA, so we can see that RTA, RTB, RTC, and RTD, this is D actually. So all of them actually have the similar, most of it is similar. All the routing tables has similar information. The only difference is the next hop and metric. So let me just snap this photo, snap this picture so we can look at it more tightly. Let's copy this. Then let me just paste it here. So do all routers have different information, same information? So the answer to that is actually the more precise answer is mostly yes. Mostly yes. Mostly yes. Because the only difference is the next hop. IP and the metric. So the reason I say mostly is because all the routing tables have the same amount of networks. The only difference is the next hop IP. Actually, the port also is different. The only difference is, excuse me. The only difference is the port used by the networks, next hop IP, and the metric. Actually, let me just answer this no, actually, because that's the only. Let me see. Actually, I just answer mostly yes. That will be a more precise description, because mostly yes, as all the routing tables, as you can see, have the same amount of network. Yeah, the same amount of network. And then the only difference is the port, the next hop IP, and the metric. That's it. So I think my answer for step 4A is that's my answer. And then moving on to step 4B, write down what RTC and RTD routing table information, the next hop IP and metric to the network 172.16.224.0/24. So since we think we don't need RTA and then RTB, so we only focus on RTD and RTC. So the next hop, so RTC, next hop, IP, and the metric, and just similar format for RTD also. So this network here, this is the network here, 172, I think it's this one, 172.162.224.0/24. Actually, it's not this one. Actually, I think it's 23, actually. Yeah, I think it's 23. Never mind. So it's this one. So the next hop IP address is 172.16.130 and .5. As for the metric is 120/1. As for the RTD, to the network 172.6.224.0/23, it will be 172.16.230.13, and the metric is 120/2. So that will be my answer for B. Step 4B to be precise. And step 4C, what is the difference can be C? What is this? So step 4C, the difference is the main difference is actually the metric, as it is an indication of the distance between the source and the destination of the route. The main difference is the metric, as it is an indicator of the route distance between. Actually, let me just word it this better. The main difference is the metric. The metric is assigned to a route to indicate the distance between the source and the destination. Sorry, excuse me. And then afterwards, the lower the metric, the more likely it will be chosen to be forwarded packets. So the next hop IP, this next hop IP has IP is the IP address of the router receiving the packets forward. The main difference is the metric. The metric is assigned to a route to indicate the distance between the source and the destination. Actually, let me just say, remote network. The lower the metric, the more likely it will be chosen to be for the packets. The next hop IP is the IP address of the router of the chosen address of the chosen router to receive packets forward. So that will be my answer for step 4C. So afterwards, moving on to step 4D, can all the PCs ping each other successfully? So I have to close this two first, because we are not going to use it for now. So going back to the default select, and then let me just type in the ping again. So go to desktop, terminal, actually not terminal, I'm sorry, wrong one. Go to the command prompt and then try to ping. So from PCA I had to ping to PCB, PCC, and PCD, same like last time. So to go back up here, find the IP address for PCB and attempt to ping it again. So paste it here. Okay, we can see that now PCA successfully have established connection with PCB. So let me just copy this icon. Okay. So PCA is able to establish connection with PCB. Now moving on to PCA and PCC. So let's just attempt to ping to PCC now from PCA. So copy and paste the IP address for PCC. So let me just enter it. So now PCA can communicate with PCC now, and afterwards PCA, let me just try to now ping it to PCD. So we have one timeout and then two. We have one timeout and two. Actually, we have one timeout, and then the rest is successfully sent through. So I just had to make this unsuccessful because I just not assume that it's required for all the packets to be sent to the receiver in order to consider as uh, a successful like connection between the two PCs here. So moving on to PCB, we have to establish a connection between PCB and PCC. So moving on to PCB, go to the command prompt, ping. Now, ping PCB to PCC. So PCB, trying to ping the PCC now. So we can see that PCB successfully like established connection also with PCC. So okay. So now I'll attempt to establish connection between PCB and PCD. So ping PCB, ping PCD from PCB. So enter again. So now we actually have so 100%. So we have 0% loss. So that means that all the packets are sent through without any issue. So that means it's successful. Sorry, it's a successful connection between PCB and PCD. So now I have to ping PCD from PCC. So going to PCC to the command prompt, ping. Since I already have the IP address for PCD, let me just paste it in there. Actually, no, never mind. So now let me just copy the PCD IP address again. And I type in enter. As you can see here, that PCD, so PCC is able to establish connection with PCD. That means that it's a successful. Okay, it's successful. So since we already like proven our point, so we already completed all the tables here, the table 5 here. So now I think that it's all for step 4D. Now for step 4E, reflection. What is the reason for your answer in D? So that means that I had to like think of a reason. So most of the devices are able to connect to each other due to the dynamic, due to the RIP. There is one unsuccessful connection. There's one unsuccessful connection maybe due to I think that the reason is it can be misconfiguration. Actually, there's a lot of possibilities. So the reflection is most of the devices are able to connect to each other due to the routing information protocol. and there is one unsuccessful there is one unsuccessful connection, and maybe it's due to like misconfiguration. There's a possibility actually. Hmm, let me just maybe due to hmm, maybe requires just more update, I think. Incomplete, I guess. Incomplete routing, I guess. Incomplete routing towards uh, towards PCD from PCA. So I think that will be my reflection. So that will be my reflection or step 4E, my answer for step 4E. So I think I will afterwards I will cover step 5 afterwards. So now I'm going to continue on explaining step 5 of task 2. So step 5, switch off router, RTA, and then what are the changes noted in the routing tables. So in order to observe the changes, I have to open all the routing tables. So I have to use the normal way, the usual way to open all the routing tables. So this is all the items in A. Then this is should be actually I am unable to like display everything here on in full screen, so I just have to like how do I say service. As you can see here that everything is the same amount of network addresses. So 1 2 3 9 9 9. Actually there's only 2 here. Then actually wait, it's only around this 8 here, and then this is 9 here. So that's it for okay. This is the initial. This is the initial routing tables for all the routers. So now I have to switch off router RTA. So I have to note the changes of it. So this RTA. So I think the main thing that we need to like look at is RTA, routing table RTA. So I have to go here. In order to switch it off, I have to go to this thing, go to RTA, router RTA, then go to physical, and then afterwards, here is the power button. So let me just switch that off. As you can see, I guess you can observe that. Oh, never mind. Just open it back up. Yeah, yes. So open it up back up. So you can see that routing table A has nothing now since it's switched off. And you can also observe that routing table B originally has like nine networks, and then now it only has 6 of them. And then now it has now routing table C originally has 9, now it only has sorry, originally routing table C I think has around 9 reduced to 6, and for routing table D 1 2 3 4 6 7 8 9, so it sort of remains also remains 9. So we can see that actually that there is actually a lot of change in the routing tables when routing table A is switched off. So let me just snap it, and then afterwards copy this one. Paste it here. So we just answer this. When the router RTA switch off, the routing table for RTB and RTC changed, while RTD remains unchanged. Actually, I need to be more specific, so switches off. The amount of networks in routing table, in the routing table for RTB and RTC reduced, while RTD remains unchanged, and the routing table for RTA is empty now. It's empty. So that will be my answer for step 5. Now let me just check the configurations. It's configured normally. Okay, it's configured normally, so I don't think that's the issue there. So now, moving on to step 6, switch on the router RTA. What are the changes noted in the routing table? So as you can see here, routing table, I already explained that RTB and RTC got their amount of networks reduced, and then the RTA just straight up doesn't have anything. And then the routing table for RTD that remains unchanged. So now I have to switch the router back on. So you can see here that all these red triangles indicate that packet's gonna be sent, I think. So let me just change back. Switch on the router RTA again. So let me just switch it back on. And then we can see that it instantly, actually it doesn't instantly. It requires some time to reboot. It requires some time for the routing table to reboot. As you can see here, the routing table for RTA is slowly but surely like filling up. So yeah, everything is filling in again. So there's actually 1, 2, 3. So there's 3 9s. Actually 9, 3, 6, 9, 3, 6, 9, 3, 6, 8. So when we switch back on route RTA, we can notice that the changes. So of course, when we switch back on RTA, we can see the routing table for RTA just returns from the original. Let's paste it here so you can observe it. So for the routing table for RTA, you can see that all 9 of the networks from previous is actually just returned, and then all the other routing tables also return to their original state. So previous before I close it, before I switch off the router RTA. So let me just answer this. So let me just copy the answer here so we can just make some changes to it easier. So switches back on. So when the router RTA switches back on, the amount of network for RTB and RTD is The amount of network in the routing table for RTC is increased. Restore. I mean, restore is better. Restores to their original amount of networks, while RTD remains unchanged, and the routing table RTA gets restored to its original actually the routing table for RTA I can say restored to its original state before switching, before the closing, before the switching off of the RTA. Actually, let me just power off. So when the router RTA switches back on, the amount of networks in the routing table for RTB and RTC restores the original amount of networks. While RTD remains unchanged, the routing table for RTA restores to its original state before the power off of the before the power off of the router. Actually, yes. Let me just check RTD for a moment, so we can see that. It's better to see it like this. So we'll compare one of them. Actually, if we see closely that one of the matrices, this metric here, actually changed, and these two also change. So actually, there's actually a lot of changes. So we can see that RTD have so the network for RTD, for network 172.6.2.62.4.0 So the only thing that is like different is 230. Have their metric reduced or changed to, actually just change to 1/2. This one is 2, this one is 2 and 1. Respectively. So I think the changes that those are all the changes for step 6. That's all. This is my answer for step 6. Actually, I need to go back to step 5 because I just realized that RTD actually has some changes to it. So it's that previously it's actually changed to 120/16. So that means that I didn't see it previously. So that's an oversight for me. So I'm sorry for that. So this is my changed answer for step 5. When the router RTA switches off, the amount of networks in the routing table for RTB and RTC is reduced. The network 172.16.224.0, 172.16230.0, and 230 and 4 in the routing table. RTD have their matrices changed to 120/16, and the routing table of RTA is empty. So for step 6, this is my answer for step 6. When the router RTA switches back on, the amount of networks in the routing table for RTB and RTC restores the original amount of networks. And these three networks here, so these three networks here, this one, and this one, have their matrices changed to 120/2, 120/2, and 120/1, changed to these matrices respectively. So the routing table for RTA restores to its original state before the power off of the router A. So that would be my answer for step 6 now, and this is the proof for it. So now moving on to step 7, reflection. What have you learned in this task? So throughout my experience for doing task 2, I learned that IP is a dynamic routing protocol. It's a dynamic routing protocol that can determine the best path of the between the source and the destination device from the source based on the metric of each route. So routing information protocol is a dynamic routing protocol that can determine the best path from the source to the destination device based on the metric of each route in a network and it actually chooses based on how many hops. So for example, how the RIP works is that it will choose, like example, if PCA wants to send like send a message to PCC, so it had to go to this. There's actually two routes. So yeah, you can either go to PCA can go to RTA and RTB and RTC in order to go to PCC, or it will just go from RTA to RTC. So we just choose the RTA to RTC route because it's the shortest. So RIP uses the hop number. I think that's called hop number to determine the shortest path to the destination from the source. So this is what I learned throughout the task. And even if one of the routers is powered off, the routing tables for all routers will update quickly. Excuse me. Update quickly. As updates to all our routing tables are periodic. That's why when we like switch on the router here, we actually just need to wait for a bit in order for them to completely like change all the routing tables. So I think that will be all. Actually, let me just check again. RIP is a dynamic routing protocol that can determine the best path from the source to the destination device based on the metric of each route in the network. RIP uses the hop number to determine the shortest path to the destination from the source. Route, actually it's better for that. The source route. Destination. Source route. Even if one of the routers is powered off, the routing table for all routers will update quickly. The routing tables for all routers will update quickly as updates comes periodically. Actually, maybe that's really better. As all routing tables updates periodically. So I think that will be my answer for step 7, reflection. And I think I'm done with lab 3 task 2, and I'm going to move on to lab 3 task 3 afterwards. So now I'm going to continue on doing lab 3 by continuing lab 3 task 3. So in task 3 I had to learn about dynamic routing configuration, but now it's all SPF, or the full name I think is called Open Shortest Path First. So make sure that you have all the routing tables on display on one side as before. As you go through the steps, look at the changes happening in the routing tables. So step 1, on all the routers, do the following. So I had to go to the CLI tab again, and then configure every router. So at this point, let's say, let me just do the routing table here. Just put routing table here. Excuse me. So these are all the routing tables. So this routing table here, I'm just gonna note the first. I'm just gonna note the most basic thing first. So step 1, on all the routers, do the following and just configure it. So this routing table for RTA, RTB, RTC, RTD. So there are 4, then actually 4 afterwards. 9. 4 is 9. 4, and then afterwards 9, afterwards 4, then 8. So this is the initial. So let me just go to each router here, and then go to the command line, or it just, okay. So we have a clean one. So now enter. I think we have to enable it first. Enable it. So configure terminal, and then config no router IP. So as you can see here, our RTA is from 9 reduced to until only like 3 of them. So exit, then afterwards type in enter again. So copy this one. Reverse the TA. Oh, our TA is still open. Just close it for now. So RTA copy running. Okay. So I'm done configuring for RTA. As you can see, it already has some changes. Just close it now. Afterwards, go to RTB. Oh, just have stuff in there. Previously, need like type in the things still here. RTB, how to enable it again. Even though it doesn't say how to, how to enable it in order to change this arrow here to this. So configure terminal, no router, IP, exit. As you can see, it also changes. Exit, enter again, paste it in, enter again, enter. Okay. So I think that's all. And afterwards, go to RTC, enter, enable, configure terminal. Afterwards, no router RIP. As you can see, it's already also reduces from 9 to 4 only. And afterwards, go to actually exit, and afterwards can press it in. Okay, that will be done. That will be configuring done for RTC. Actually, need to check the FTP. Exit. Yeah, I did. So moving on to RTD. Okay. Enter. Enable. Configure terminal. Afterwards, no router IP. As you can see here, I just saw that routing table D also changes. Yep. So exit, paste it in. Yeah, that's. So I'm done with. Actually, I'm done with step 1. So I'll read all the routers the following. Actually, I'm done with step 1 of task 3. Now I'm going to move to step 2. Copy the images of the routing tables for each router. So since you already observed the changes for each router, for each routing table, the routing tables of each router, now I'm going to like just record the initial state of it also. So RTA, RTB, RTC, and RTD. So let me just snip it one by one. This is done. TB. It's RTC. And then last but not least, RTD. Close it for now because I want to look at the thing clearly. I guess I can make it a bit smaller, but move it down a bit. So that will be my answer for step 2 of task 3. Now moving on to step 3. For router RTA, click the CLI tab, copy the following text into the command line interface. So let me just close that for a second. So let me just first open the routing table for RTA, put it here. This is already like configuring for routing table A, RTA for now. So now I have to configure the terminal. So go to here, same page here. So configure, since the symbol here is already like hashtag, we just have to follow the command. So configure terminal. Copy this one. Copy this command. Paste it in here. Enter. Afterwards, I have to copy and paste the following commands. Afterwards, and afterwards, enter again, paste in the thing, and then enter it. Okay, that will do for step 3. And task 3.1, paste the image of RTA routing table here. So let me just close it for now. So as you can see here, RTA routing table here doesn't change. So it doesn't change, I think. Just a bit. Compare it. The picture. Actually, it's fine anyway. Let me just compare with this one. So it actually doesn't really change anything yet for now. It's fine for now. So moving on, okay, this is the routing table for RTA, and then now moving on to task 3.2. Does RTA have a path to all the different subnet? So if we see the routing table, no. The answer is no. So in order to prove that, to try to ping on PC3 actually. Okay, for now, since that we need to try to prove that RTA doesn't have a path to all the different subnets. So I have to try to ping to different TCs and I need to jot down my results. So now open PCA again, go to the command prompt, and afterwards go then try to ping to PCB again. From PCA to PCB, PCC and PCD. Okay. So I have to go back up here again. Find the IP address for PCB. Paste it in here. So from PCA, I had to ping to PCB. So let me just try to do that. Quest timeout. So we can see that PCA is unable to reach PCB, so it's unsuccessful. And PCA, okay, now I'm going to continue on pinging PCA to PCC. So move it up here, copy the IP address for PCC. So now I'm going to ping to PCC from PCA. So here we can see that all of the packets is unable to reach the host. So we can safely determine it is unreachable. So moving on to PC, we need to ping PCA to PCD. So now moving back up here, trying to find the IP address for PCD. Copy this, copy, and ping. Now PCA is going to ping PCD, so enter. So same result, it's unsuccessful. So that will be my answer for task 3.2b, since I already proved it through here. Since all of them are successful. So moving on to step 4, configure the other routers with OSPF routing algorithm. So I have to follow afterwards. So in order to configure it, okay, step 4.1. For router RTB, click the CLI tab, copy the following text into a command line interface. So I'm gonna, continue on. So since it's already hashtag, so I'm gonna type in enable. Configure terminal. Actually, let me just do that. Then afterwards, paste it, and then I'm gonna proceed to copy and paste the following commands into this command line interface here. Actually, beforehand, I need to open. I think I need to open the thing table. Just in case there's any updates. Quite kind of packed, so sorry. So moving on, pasted the other one. So this will be the second, actually, yeah. So I'm gonna enter it, and then afterwards copy this command here. Actually, paste it here. Oh, never mind. So it's enter again. And I think that will be all for now. So it will be N, and then configure console, and enter again. So let me just copy this one also. Copy this command here. Paste it in here. Okay, the configuration for RTB is already done. So you can see here RTA just updated, and RTB also updated. So how many are there? 1, 2, 3. So actually 5 now. Five. Yeah, there's already 5 now. So moving on to configuring RTC. So step 4.2. For router RTC, click the CLI tab, copy the following text into the command line interface. For now, we are going to configure for RTC. So click this one, enter. And now, oh, I have to enable it for now. So I have to configure terminal. Okay. So now, excuse me. So now I have to this copy and paste the command lines here. The second one, the third one. Oh, third one. The fourth one. And the N. So now I'm gonna copy this code line here, this command here. I'm just gonna enter it again. Enter. Enter again. So I'm done configuring with RTC. After RTC, and then let me just observe the changes to the routing table. So you can see that the routing table is increasing. So the amount of network is increased to 7. Originally it's 6. And this the routing table of RTC is also increasing to 7, and this one is also 1, 2, 3, 4, then 5, 6, 7, 8. Yeah, that's 8 here already. So moving on to configuring, I think it's RTD, yes. So step 4.3 for router RTD, click the CLI tab, copy the following text into a command line interface. So to configure RTD. So in order to do that, go to here, yes, it's conveniently to this CLI tab already. So let me just enter, enable, so it will change to the, what can I say, hashtag symbol. So configure terminal, and then copy this command here. And now let me just copy the rest of the command into this, into the interface here. So copy the second one, paste it in here, let's enter. Oh, that's it. So end it. Then the last one is, I think I just saw. Yes, this one is just updated. So enter again. Enter. Okay. I think that is all for step 4.3. So okay, I'm gonna close this for now. So we can see that here we have 1, 2, 3, 4, 8. So we have 8 here. We have 8 here. We have 8 here, and then also here we have 9 here. Yeah, we have 9 here. Copy the now moving on to step 5. Copy the images of the routing table for each router and paste it here. So to like, sorry. So now I have to copy the images of the routing table. TA towards the service template. OTB, C, OTD. So first I'm gonna snapshot RTA first. So this RTA. RTB now. Snapshot for RTB. Do the routing table RTC now. And now finally I'm gonna do the snippeting for, sorry, I'm gonna do the snippeting for RTD. So I think I already answered step 5, copy the images of the routing table for each router and paste it here. So we have routing table A, we have 9 of them. Routing table B, we have 8 of them. You can see 8 of them. Routing table D, we have 8 of them. I think that's it for step 5. And I think I just gonna like I'm gonna explain step 6 afterwards. Now I'm going to before I'm going to explain step 6, let me just open all the routing tables for the of each router. Because I didn't realize that all my this one is fine. Routing table for RTA is actually fine, and RTB. Just realized that it's not really complete, so let me just retake it for now. RTB. RTB. Why did I close it? Oh no. Oh, it's embedded in it. RTC. And last but not least, RTD. So now, after I clean up a bit for step 5, let's just move on to step 6. So step 6, I have to switch off the router RTA. And what are the changes noted in the routing table? So now, since I already like open all the routing tables for the routers, so let me just kind of arrange them. So note that actually it has 8, this has 8 as well, and then this is 5. No, actually this is 9. So 4, and it's 9. So also 8. So let me just now, as like previously for task 2, I have to switch out the router RTA. So in order to do that, I have to go to router RTA, go to physical, and then afterwards let me just click on this power button here and to switch off RTA. Let me just do that. As you can see, routing table for RTA just instantly there's nothing in there anymore. So for RTB, as you can see, previously there's 8, so now it only has 3. So sorry, it only has 5, And for RTC, previously as 8, okay, now it has 5 now. And then for RTD, you can see that previously we have RTD, RTD we have previously we have 9, I think. Now we only have 5 of them. So in conclusion, that every routing table have their network. The amount of networks in each routing table is reduced. So let me just arrange it properly. Let me just take a snippet. Okay, that's the first thing I saw. So let us compare it with the other ones, from the previous ones. So we can see that everything from RTA is gone, and then I think every information of RTA. So RTA originally has this, this, and this. So afterwards, if everything is gone, so yeah. Okay, we can see that. Actually, Type C. I forgot to mention about Type C. Type C network actually means that it's referring to the interfaces directly connecting to the router itself. So that's why I'm looking at the Type C. I'm looking only at the Type C because Type C, if Type C means that originally the router already has them, and then Type O means that the router learns the IP address from other routers through the OS, PF protocol. So now I need to mention about all the changes. So the changes are that all information in routing table, routing table RTA, the RTA is empty. All information in routing table RTA. I can say, actually let me just do this. It's not empty. Empty. All information about all information actually routing table RTA is not empty. All information about RTA, all information about networks in RTA in other routing tables are deleted as well, since we see that every we just saw that every when RTA switch off, everything in here just for lack of a better word gets deleted, and then every network that is related to RTA is also deleted from the other routing tables. So I think this is my way of explaining it. So this is the answer for step 6. So routing table for RTA is not empty. All information about the networks in RTA in the other, actually off RTA is better. RTA in the other routing tables are deleted as well. So I think that's the answer for step 6 now. So afterwards, step 7, switch on the router RTA, wait a few minutes, what are the changes noted in the routing tables? So now I have to switch on, just shut this in first. I have to switch on RTA again. So let me just click on this, go to the physical. Now I don't need to click anything, I just like go here and then click on this power button to open it. To switch on RTA again. So let me just close that. So it just wait a few minutes. So we just need wait a few minutes. Okay, this is updates here now. So now the other tables should have the other routers should have their routing tables filled in already. A few more minutes. Yep, as you can see that RTA, the routing table for RTA, RTB, and RTC just returns to normal, including RTD also. So that means that everything returns to normal, to the initial state. Initial state is a better word for it. So let me just answer step 7 now. Switch on the router RTA with a few minutes while the changes noted in the routing tables. So let me just paste the picture here first. So now compare the pictures to our routing table. Routing table A, does it change anything? Let's check through it. Doesn't seem like it is changing anything, so it's fine. Okay, that's routing table RTA for now. So now RTB, I had to check. Okay, move this here for now. So for RTB, get through this. Yes, RTB is the same for everything. RTC, same as the initial state. RTD, RTD now. Check through it. So there's nothing like different between them. So we can say that um, all information in RTA reappears after a few seconds. So after a few seconds, and RTA restores to its initial state before switching off RTA. So all information in routing table RTA reappears after a few seconds and RTA restores to its initial state before switching off router RTA. All other routing tables have their network. All other routing tables actually, let me just bullet this. Information about the network of RTA networks of RTA have also been restored to all other routing tables. So that will be my answer. So the step 7's answer will be all information in the routing table RTA appears after a few seconds and RTA restores to its initial state before switching off router RTA. Information about the networks of RTA have also been restored to all other routing tables, as we just observed just now. So step 8, the reflection. What have you learned in this task? So in task 3, I learned that actually, before that, just change the format. So in task 3, we learned about the OS, the open shortest path first. This protocol is also a dynamic, how can I say? It's also a dynamic routing protocol. Yes, dynamic routing protocol, and it uses its own like its own, how can I say, shortest path think algorithm in order to determine the, how can I say, to determine the best path from the source route route to the destination. So the destination. I say this is because that if you like remember what I say around in while I'm doing task 2, you will see that the matrix is actually like the matrix here is 65, 109. But if we look back at task 2, you can see the metrics are actually much more lower, like 1 or 2, 2, that's it. So that means that it proves that the OSPF protocol indeed like uses own like shortest path algorithm in order to determine the best path from the source route to the destination. So updates. So the updates for this particular protocol only triggers updates only triggers for the um for the routing table of all routing the routing tables of all routers if there are any detected changes to a routing table. So the OSPF protocol is also a dynamic routing protocol. It uses its own shortest path algorithm to determine the best path from the source route to the destination. Updates only trigger for the routing table of all routers. Actually, just put it like this. So updates only trigger actually the routing tables of all routers will update only if there's any detected changes to a routing table of a router. So I think that is all for step 8 reflection. And I think, yeah, this is the end of lab 3. So I guess I have to thank everyone for listening, actually for watching me to explain Network Communication Lab 3. And thank you everyone for listening.